Today I'm going to present to you VENOM. That is a new sparse format compression that allows the execution of sparse matrices with arbitrary levels of sparsity on sparse tensor cores, which are natively restricted to 50% sparsity. So first of all, let's take a look at this illustration that depicts the year-by-year growth in size of some popular machine learning models. So as we can see, there is an exponential increase in the number of parameters, and this trend results in tasks associated with these models, such as training, requiring money investment that soar into the millions of dollars. So as an example, the cost of training GPT-4 is expected to be around $100 million. So furthermore, when deploying these models at any reasonable scale, the cost of inferences exceeds by far the cost of training. So this cost is not just related to their training, but to their entire lifetime. So the question here is it imperative to have such a vast number of parameters, or is it feasible to construct lightweight versions of the original dense models that maintain accuracy with minimal to no degradation? So model sparsification is a research area that tries to answer this question with the intuition behind that not all the features are always relevant. State-of-the-art pruning techniques have successfully reached sparsity ratios of around 90% in well-known models such as BERT, ResNet, or GPT, with a small to no impact on accuracy. Consequently, we are transitioning from dense to sparse computation, where general matrix-matrix multiplications evolve into sparse matrix-matrix multiplications, where now one of the operands is going to be sparse. However, note that sparsity in machine learning is very different from sparsity in traditional HPC scientific computation. Here, the sparsity levels in machine learning are much lower, and the matrices are quite irregular, right? This is an example of sparse matrix from scientific computation, and in machine learning, they look like this. So as a consequence of this irregularity, the existing GPU kernels tailored for sparse computation in machine learning are still inefficient, especially if we refer to half precision and tensor core execution, which require a very regular data layout to use this hardware component. So let's first take a look at this critical piece of hardware, the GPU tensor cores. So as you know, NVIDIA increases its computation capabilities in every new architecture, and this gain has been achieved by different number representation and sophisticated manufacturing technologies. However, one of the biggest gains is the introduction of tensor cores, which allow performing big computation in a single instruction, such as matrix-matrix multiplication, reducing the overhead of fetching and decoding multiple instructions, right? So from the Ampere architecture, NVIDIA introduced what it calls structural sparsity, which promises a 2x speed up over the original tensor core performance. So now we can execute structural sparse matrices on what they call sparse tensor cores. Great, so now in our original dense models, we can remove some neural connections or drop some weights and get a lightweight sparse model representation of it that can be executed on these specialized vector units. However, if we want to take advantage of these new sparse tensor cores, the distribution of non-zeros will have to accomplish a very specific format, right? So that structure sparsity format is called by NVIDIA the end-to-end format. And the table on top here shows the supported end-to-end values for different number representations. So let's focus on half precision as one of the most extensively used number representation in machine learning models. So with 2 to 4, we first have to divide our matrix into vectors of 4 consecutive elements. And then for each 4-element vector, we will select the best 2 elements according to different criteria here. In this case, in this example, based on their magnitude. So as a result of this pruning, the new sparse matrix will be compressed into 2 data structures. The blue one contains the values we selected, and the purple one contains the positions that those 2 elements occupied within the original 4-element vector, right? So then we do the same with the next vector of 4 elements, and we will repeat the process until we finish, until we have pruned all the vectors of 4 elements here. Okay, so now that we know the NVIDIA end-to-end format, the next question is to answer is how is this sparse format mapped onto hardware? In this figure, I show a sparse matrix A compressed according to a 2 to 4 pattern and a dense matrix B. So in order to answer this question, let's calculate the first output element by multiplying the first row of A and the first column of B. And this illustration here shows a simplified representation of how the sparse tensor cores work and how the sparse metadata information is mapped onto hardware. So the metadata indexes will be used by the new hardware components included on Tensor Core for structural sparsity to take just the elements of B that are necessary to perform the computation. Then the Tensor Cores will perform the dense multiplication as usual. However, as you probably noticed, the end-to-end formats supported by NVIDIA only allow 50% sparse matrices. So 1 out of 2 or 2 out of 4 elements are selected. And this represents a new challenge, since sparsification techniques can sparsify to much higher sparsity levels with no accuracy degradation, but sparse tensor cores are restricted to 50% sparsity. So to address this question, we should start by exploring some of the existing sparse formats available, along with their respective advantages and disadvantages. So blockwise format defines a 2-dimensional block of non-zero elements, and it favors tensor core execution since the final structure will be very regular, will be a very regular sparse matrix, right? So especially if we use big block sizes. However, this format is very restrictive in the way selection, and which makes the accuracy drop. And furthermore, there is no native hardware support for it. Then we have vector-wise pruning, which selects 1-dimensional blocks of non-zero elements. And this format increases the way selection flexibility, which favors accuracy and allows us to find better accuracy to performance trade-offs. However, the performance is still limited by the irregularity of the resultant sparse matrices, and the speed up over the dense counterpart versions is still far from the ideal. So once again, there is no hardware support for this sparse format. And finally, we have the end-to-end format that we already described. And this is a very flexible technique which greatly preserves the accuracy, but the existing hardware support is limited to 50%. So this is precisely the moment when VENOM steps in and takes a role, right? So let's try to create a new sparse format that fuses the best properties of each of the existing ones. So the flexibility of the end-to-end format is clearly the most interesting choice in terms of accuracy, but also performance if we want to take advantage of these specialized hardware units for sparse computation. So let's start by dividing the original dense matrix into blocks of size V by M. Then for each V by M block here, we will select the best 4 columns out of M. And this way we are limiting the number of columns with non-zero elements on each V by M block from M to 4. And finally, we can apply the original 2 to 4 algorithm for each set of B by 4 blocks of elements. As a consequence, the entire matrix can be perceived as a 2 to 4 sparse matrix with less significant blocks of V by M minus 4 dimensions being dropped. So now we can execute this matrix on sparse tensor cores and apply the same procedure to any M value, or in other words, to the entire sparsity range. So it's important to highlight here the flexibility of VENOM. So within every V by M block, we selectively focus on a specific subset of columns reducing the restriction of blockwise pruning. And then these chosen columns are not densely packed, and enabling us to prioritize and pick out the most impactful weights, improving the flexibility also with respect to the second option, the vector-wise pruning. So as we will see in the evaluation, this flexibility allows VENOM to use large p-values of 64 or 128. So the next step to study here is how can we efficiently compress the VENOM format, right? So to do this, we will just need to add a third structure that is called column lock. And this structure will store the indexes of the columns selected for every V by M block, highlighted here now with this yellow color. And then, as usual, the non-zero values structure will store the values of the preserved weights. And finally, the M indexes structure will now store the positions of the two preserved weights within the selected four columns. So in this example, for the first four by M block, columns 0, 2, 5, and 7 have been selected. And then in this set of four columns, the elements preserved are in the first row correspond to the position number 0 and position number 2. Great, so let's now talk about the second big contribution of this paper. So to exploit the VENOM format, we present a sparse linear algebra library that implements the SPMM routine supporting the VENOM format. So the design of Spatha has been divided into three main stages related to the data movement, the computation, and the result storage. So first, let's take a look to the first stage, the data movement. So to calculate the first output element here, we multiply the first row of the sparse matrix A by the first column of the dense matrix B. However, as we already described with the two structures of the original NVIDIA end-to-end format, we cannot map this computation onto sparse tensor cores. So at this place, the column lock structure plays a fundamental role, and this software engineer solution will be used to filter only the elements from V, so we can use those elements as inputs to the sparse tensor cores and execute the product as we were using a 2-to-4 format. So the idea of just having some non-zero columns on each V by M block will allow us to just load the values of B that are strictly necessary in the computation, like this. And this way, we can reduce the data movement linearly with the sparsity level, which is a critical aspect in terms of scalability. And the length of P here will be critically in the overall process, as we will see later, because this is a memory-bound problem, right? So now we are going to describe all the details of, we are not going to describe all the details of the Spatha and library in this presentation, but you can find an in-depth description about the three stages of the Spatha library design in the paper. So this involves the software data movement pipeline, then a low-level description of how the elements are mapped onto sparse tensor cores, and the data layout proposed to store the results, avoiding bound conflicts and using the wider memory instructions available. Okay, so let's talk now about some preliminary results. So maybe some of you are asking, okay, so you can execute sparse matrices with arbitrary levels of sparsity on hardware designed only for 50% sparse matrices, but what about the overhead of the new third structure added to achieve so, right? So these results show an ablation study about the performance of Spatha with and without the column lock structure. And as we can see, the overhead of the column lock is negligible in the overall performance. It is slightly higher with super sparse matrices like this 2 to 100, but sparsity levels in that range are not realistic in machine learning problems. So Overall, the speedups get close to the ideal as we increase the arithmetic intensity, obtaining up to 37x performance with respect to cuBLAS. So these speedups ratios are promising, right? But so far we have described the Ben-Nun storage compression format and how it can be mapped onto specialized hardware units to maximize this performance. But there is still an open question here, right? So can the VENOM format be used to prune real models with no to small impact on accuracy? So magnitude pruning is a straightforward and effective way to select the elements for removal based on their absolute value. However, the effectiveness of this method becomes more challenging to select the less significant elements to remove with structure formats or high sparsity ratio. So as a consequence, we decided to implement a second-order pruning technique to demonstrate the VENOM format. Second-order pruning represents a more sophisticated approach based on second-order information, which has been successfully applied on real models to sparsity ratios such as 90% or so. So overall, the target is to identify the set of weights Q that we can prune with minimal loss increase, while the remaining non-zero elements accomplish these VENOM format restrictions. So our second order pruning method is inspired by the original Overt paper, which defines the saliency score function on the left to select such a set of weights Q on a well-optimized W model. But I'm not going to describe all the details of Overt here because they are very well described in the paper. So let's move onto its application to the 2-to-4 format. So the Fisher matrix contains the correlations between all the weights in a group of 4 elements. So the size is 4 by 4. And then the E sub Q matrix is composed of the canonical basis vectors representing all the possible weights to prune a 4-element vector following a 2-to-4 format. So we have here six possibilities, right? And finally, all the elements for removal in this technique are selected and dropped in a single shot, which means that the target sparsity level is achieved on just one iteration. So overall, the combinations to evaluate here, defined in E sub Q, represent a computational affordable problem, and the one-shot pruning method is feasible considering that the final sparsity is just 50%. However, if we want to extend this second-order pruning method to arbitrary levels of sparsity, then the number of canonical vectors to evaluate will represent an M combinatorial problem. And if we consider that our final goal is to adapt this method to VENOM, which adds one additional dimension to the search space, it turns into an intractable combinatorial problem. So based on these conclusions, we propose a second-order pruning method on top of Overt, but tailored to the VENOM format, which overcomes the original limitation of the method with the following techniques. So first, a new pairwise approach to describe the set of canonical vectors, which removes the M combinatorial issue. This way, weight correlations will only be considered within neighbor elements, okay, which simplifies a lot the search process, but was demonstrated to be very effective and robust with the sparsity level. And a second technique, and that is a new gradual pruning setup for end-to-end sparsity, which substitutes the one-shot pruning approach of Overt. And this technique has shown to be much more effective in recovering the original accuracy when the sparsity level increases. So this is a general overview, but you can check all the details of this technique in the VENOM paper. So I think it's better to talk a bit about some evaluation results. So in this first evaluation here, we have included some other third-party libraries that make use of alternative sparse formats, so such as blockwise, vector-wise, and element-wise pruning. So the evaluation has been performed on the DLMC dataset, which is composed of matrix extracted from well-known models in the literature, and the speed up over cuBLAS is represented in the y-axis in logarithmic scale. So note that QSparseLT here, that is the NVIDIA implementation for 2 to 4 for the 2 to 4 format, is only represented at 50% of sparsity because it is restricted to this 2 to 4 format, so 50% sparsity level, right? As we can see, the performance of Spatha largely improves the performance of any of the existing implementations. However, it's important to highlight that this difference increases further when we increase the problem size, controlled in this evaluation using C, which is typically associated with the batch size. So this happens because higher problem sizes or larger problem sizes increase the arithmetic intensity and fill all the GPU resources, so we can get closer to the theoretical performance. Tiny problem sizes will spend most of the time moving data instead of performing real computation. And overall, Spatha achieves speedups of up to 25x in this example, while the best existing solution is always below 4x. And then we repeated the same experiments on matrices extracted from larger models, in this case, BERT base and BERT large. So the result in this case confirm our previous statement that the larger the problem size, the better the performance. And we can see that the performance difference between Spatha and other competitors is still more remarkable, with speedups of up to 27x here, compared to the best peak performance of 4x in the best existing implementation here. Okay, so finally, let's evaluate the contributions of this paper on real case studies. So in this case, we selected LLMs. First, we are going to start with the sparsification technique. In this slide, we show the evaluation of the proposed method on a BERT model fine-tuned on the squad dataset. And to that end, we prune the weight matrices present in the multi-head attention, highlighted on the simplified representation on the left with these white circles. And the result shows that 75% of sparsity, VENOM with a vector length of 64 improves the original dense model accuracy, while a vector length of 128 only presents an accuracy loss of 0.005%. And then with 87% of sparsity, VENOM with a vector length of 64 recovers around 98% of the original accuracy, while a large vector length of 128 is also able to recover 96% of it. Okay, and this final evaluation shows the end-to-end latency of real-world LLMs integrating the Spatha library. So the figure on top shows the performance of using VENOM with a vector length of 64, and the bottom figure a vector length of 128. And 1 to 2 to 4 here represents the baseline Spatha implementation for 50% sparsity, and 2 to 4 is associated with QSparseLT. Remember that QSparseLT is restricted to 50% sparse matrices. So the tensor time contraction in BERT large and GPT-2 is around 10x. However, in overall terms, this improvement is limited by the time that the gem operation takes in the overall latency in these models. So around 50% of the time in GPT-2 large and very large. However, in GPT-3, the matrices are much larger, which affects the impact that the gem has on the global latency. Okay, So this way, a tensor core construction of 11x is translated into an end-to-end reduction of up to 3.20x.